just need a quick check. You are currently doing the CRISPR practical.
Yeah, yeah, yeah.
Yes. With mutations in it and things like that.
Yeah.
So where you introduce mutations. Good. 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 Excellent.
Are you planning some? Oh, I got what you're planning.
No, you don't. Nobody knows what I don't know what I'm planning. So, I might help you a little bit. What happened to the rest of the? There should be 26 people here.
They're away, I think.
Sorry?
They're on their way.
They're on their way. Good. I'm very
They're
pleased.
using the buses. Usually the bus doesn't come on time.
I know.
I come cycling actually.
Oh, okay.
To reduce all this stuff. I have to tame myself down because I wake up with a lot of energy. Just to turn bearable for us.
I wish I had that energy.
You do?
Good morning.
Good morning.
Good morning.
Okay.
Good morning. Good morning.
Oh God, yeah.
Rush for the I have one sometimes. I should actually use school. Morning.
Good morning. Oh, limbo. Two, three, 4, 5, 6, 7, 8. Well, 8 is good. 8 is definitely good. 8 out of 26. Well, that's yeah, absolutely, absolutely. Do the codes work? Please check. But they work. Oh, fantastic! Thank you. And I notice a rather interesting gender distribution. Good morning. 10 students, one of which is male. Or, I think, well, that one needs to be very careful with that, depending on how people identify. I don't want to make any assumptions. Yeah, but it's an interesting. With 10 students, how many males would we expect? Just, if it was a sort of a randomly, 10 students, how many males should there be? 5. Well, 5. How did you do that? How did you calculate that?
I didn't calculate it. It just was part of my soul. No,
But you are right.
Well, I just.
So you calculated the number 10, and you said, well, it should be 50% male, 50% female. So 50% of 10 would be 5. Keep that in mind, because we will do that now.
Okay.
11. Good. Okay, let's make a start. Fantastic. Most wonderful good morning, ladies and jelly beans. And welcome to yet another session. I know it is on your timetable. Dr. Mulligan is supposed to do that, but we sort of made don't want to say a deal, but we arranged that I'll do another statistics session with you today, and tomorrow there is a session which also I will take, and in tomorrow's session I will tell you about the next assessment that is going to hit you. It is, I think it is called presentation or something like that, but don't worry, you don't have to do a presentation. Or I will open the assessment tomorrow, and tell you more about what it is, but it is basically a preparation for you guys for the big thing that is going to hit you in the summer, and that is your dissertation or your research project. And the assessment is actually tailored to sort of get you fired up and provide you with the tools. So it's not just an assessment, it is also something for you to, for your learning. Please make sure that you register your attendance. I'll show the codes later. And what I want to do oh no, before I forget, all of you have submitted the first assessment, the peer review assessment. And I have to say that I was generally very pleased with you guys. I think the average score was 78%. So yeah, not bad at all. So well done. But keep this sort of that knowledge about statistical tests, because you are going to need that for the future, for your future as scientists, and also for your dissertation project, where it will certainly come in quite handy. Okay, so again, these are the codes. And what I want to do with you today is I want to discuss with you something that you've probably done, but perhaps not so back still. Remember how it's done. It's about the different chi-square tests. Yes. So it is about chi-square tests. I think you do that in school do you do that in GCSE? No, A-levels, something like that. Anyway, there are a number of chi-square tests, and chi-square tests are incredibly useful because we can apply them to a wide variety of problems. Chi-square tests usually chi-square tests deal with discrete data, for example, counts or frequencies. And they look at the difference between observed data and expected data. So here is a little example for a very common one of these chi-square tests. It is called the goodness of fit test. And the goodness of fit test actually compares observed data with the data that we would expect from a sort of a model. Let me give you some data, because then it is probably easier to see what this actually means. Just a quick question before I get myself into a lot of knots. Who feels absolutely comfortable with performing a chi-square test goodness of fit? Hands up. Not all at the same time, please. Brilliant. Good. At least, yeah, we can do something here. Okay. So let's assume that you are doing a certain practical in which you want to introduce mutations into a gene. Something like CRISPR. You're doing that at the moment? Yeah? or you have done that. And you look at clones, you look at the cells, and you sequence a certain spot. And you try to figure out, you have mutants, 100, let's say 100 clones, and you want to figure out whether there is a preference in one particular spot for a particular nucleotide in the DNA. So we could have A, G, C, and T in a particular spot, which was introduced by CRISPR, let's say. Yeah. We now want to know, does this CRISPR thing have a particular preference for a specific nucleotide? Does it, for example, like to put in A's, or a G, or a C, or a T? Right? So these are our observed data. We have an A, and we find 35 colonies with an, or mutants with an A, 20 with a G, 23 with a C, and 22 with a T. And looking at the data, what is your gut feeling? Does CRISPR prefer a particular nucleotide over other nucleotides? What is your gut feeling?
Yeah.
Yes. Which one?
A.
A. Okay. So we think that A is preferred. Yeah? Bear that in mind. What would we actually expect in terms of numbers? Well, no, if we just look at that, at the numbers here, I think they add up to, what do they add up to? 100, thank you. Okay, let's think about the expected numbers. If there was absolutely no preference, we would say, how many A's would we expect? 25. Yeah, you're absolutely right. How did you do that? So it would be 100 times 1/4. I write it like that because we've got 1 in 4 chance of an A. Yeah? And that would be 25, as you rightly say. That gives us 25. That is 25. That is 25. And together, we are also getting back 100. Yeah? Okay, so what we want to test now is, are these observed numbers, these observed counts, are they statistically different from the expected counts? And when we say that, we already have our null hypothesis, because we want to do a statistical test and check null hypothesis or alternative hypothesis. Let me just quickly bring up the codes again. So think about very quickly, what would be a good null hypothesis that you could formulate for that? Remember, null hypothesis is sort of always thinks about the population.
There's no difference. There's no significant difference in population between the observed and the.
Absolutely right. So we could say, for example, there is no difference between the expected and observed counts in the population any differences that we see here any differences seen can be explained by what? Sampling error, exactly. Can be explained by sampling error. Absolutely right. Well done. Of course, we can formulate an alternative hypothesis. We can say the alternative hypothesis in this case would be there is a difference. So there is a difference between expected. I just, you can fill in the blank, yeah. And any differences cannot be explained or can no longer be explained by sampling error only. It could be that indeed there is a preference of CRISPR for A, as we assume, right? Good. So we formulated our null hypothesis. We now set our significance level alpha. 0.05, shall we do 5%? Yeah, as per usual. So 5%. We make a decision rule. Decision rule if the p-value is smaller than alpha, we say we will reject the null hypothesis. In favor of the alternative hypothesis. On the other hand, if the p-value is larger than alpha, we fail to reject. Null hypothesis. Okay, so now we need to, in step 4, we need to calculate a test statistic. And we will then map this test statistic to the probability distribution of the null hypothesis, and we will get a p-value for that, which we then can go back and go to our decision rule, say yeah or nay. How do we calculate the test statistic for this so-called chi-squared test for the goodness of fit? The test statistic is relatively simple to calculate. It is calculated with the equation of chi squared. That is sort of a weird looking X a little bit. It's a the Greek letter chi. I think it is derived from an X. And if you try to type that, obviously, unless you have got a Greek keyboard, people usually just simply write it as a capital X or something like that, if you can't find the chi symbol. Chi square is given as the sum of the observed values minus the expected values, squared divided by expected. Looks a little bit wild, but the calculation is really simple. And we can do that for our little example here. So here we put the observed minus expected divided by expected and square this. Okay, so for the first one, we have 35 minus 25 squared divided by 25. So the 35, that is our observed, minus the expected, squared divided by the expected. Yeah. Next one, we have 20 minus 25 squared divided by 25. Next one, what do we get? 23 minus 25 squared divided by 25. Last one, 22 minus 25 squared divided by 25. Yeah, happy? Pretty straightforward. Okay, so what have we got? We have 35 minus 25, that's 10. 10 squared is 100. 100 divided by 25 is 4. We have 20 minus 25, that's 5. 5 squared is 25 divided by 25, that's 1. (23) minus 25, that is 2. Squared is 4 divided by 25. And 22 minus 25 squared, that is 3. Squared is 9. 9 divided by 25. Yeah, happy with that? And all we need to do now is we just add them up. 4 plus 1, that is 5. So that is 5. And is it 13 over 25? Yeah? That is our chi-square value. What did I calculate that? That gives us 5.52. So in our case, chi-square value is 5.52. Okay? Pretty easy to calculate that. We now need to map this onto a chi-square distribution. And chi-square distribution, like the t distribution, come in a number of different sort of shapes, because like the t distribution, a chi-square distribution depends on the number of, or on the degrees of freedom. So chi-square depends on degrees of freedom. In our case, in this goodness of fit, the degrees of freedom are just simply the number of rows that we have minus 1. So we've got ATCT, that is 4 rows. We don't use the header. So we have 4 rows, and therefore the number of the degrees of freedom are 4 minus 1. It's 3 degrees of freedom. And if we want, we can use actually a graphical solution, if you like. Here would be the chi-square values. And this particular distribution probably looks like a little bit like that. It's not symmetrical. It has this funny shape. And if we used a, so that would be a chi-square with
What is the y-axis?
3 degrees of freedom, and that the y-axis would be the probability. I just show you the principle because nobody in their right mind would use a sort of a graphical solution. You would look up the chi-square value in a table, or actually you would use Excel to find that. So what we are basically looking for is, if we've got this chi-square value, let's say of 5.52, we ask, what is the probability of finding this value or a larger value if we map it onto that? So the question is, what is the probability of getting this test score or a larger one if we put that onto our chi-square curve? We are not asking whether we get anything smaller, because the weird thing with the chi-square distribution is that it is sort of, here is 0. It can't get a negative value for chi-square, and therefore we always look at what comes up with on the right side. Now in Excel, let me see if I've got, no, I haven't got sheets on. Aha, yeah. We can actually use, I can't, let me write that down, what the function in Excel would look like that does this calculation. It is chi square dist RT. This RT stands for right term or whatever. And it takes two arguments. It asks for the chi-square value and the degrees of freedom. So in our case, it would be 5.52, and we said it is 3 degrees of freedom because we've got 4 rows. So we can put that in, and that gives us the p-value. Let me quickly go over to this one here. Let's see what we get. So we said we've got 5.52, and we've got 3 degrees of freedom, yeah? That gives us our p-value. I've done that right. And the p-value is 0.137. 0.137. You know what's coming?
Well, I'm irritated because you're adding the sum of it, so altogether they're not significant, but A on its own. P-value
equals 0.13, what was it, 47 or something like that? 137, thank you. My memory is fading. So now we go back to our decision rule and say P value is certainly larger than alpha. P value is larger than alpha. We fail to reject the null hypothesis, right?
No.
The conclusion is?
There is a preference. There is significant. No, right? Oh, no, you failed to reject it. Yeah.
We failed to reject the null hypothesis. So there is no difference between expected. Yeah? So let's write that down before we get totally confused. We fail to reject null hypothesis. This means no difference between expected or between observed and expected observation or data. And therefore, since we said the expected are when there is no preference, our conclusion must be no preference for a particular nucleotide. CRISPR takes the nucleotides at random, doesn't give a flying flamingo, where it's got an A, a T, a C, a G, it just grabs something, wax it in. Right? That is what this test showed us. Goodness of fit. I'm very pleased that your gut feeling was wrong.
I'm not pleased.
And that's because that shows us that sometimes don't trust the gut feeling. Yeah, makes sense? Goodness of fit is a really simple but quite powerful test, actually. And these chi-square tests are feature very highly in the statistical world.
I have a question.
Yeah.
So, asking for the significance, but you're including all four things. So,
yeah.
Is there a way to isolate the A?
Absolutely, it's an excellent question, and that's a very common thing that people do. That they say, I want to know whether there is a preference for A. Yeah. So what I can do is, I can say, where am I here? I can say I pick just A, and so I say A observed 35, others 65. Expected 25, others, what do I expect? 75. So I could do now a chi-square test. The degrees of freedom change. How many degrees of freedom do I have now? 1, exactly. So I would have only 1 degree of freedom. But with that, I can isolate just 1 nucleotide.
Yes.
You have to include all the others. Yeah.
But you're including this. And if 3 out of 4 of them are not significantly different than expected.
In this case, you just simply say, I don't care what they are. Yeah. I just want to know, is A. Is a focus on A. That is what you do with that. In this one here, you say, is there any difference between the different nucleotides? Here, you say, is A preferred? Slightly different, but from the principle, exactly the same. Happy with that? Make sense?
Yeah.
For those of you who want to do it in R, I tell you what, I'm not going through that code. That's boring. But you can very easily do that in R. It gives you you input the observed, the expected, can calculate the chi-square statistics. You then can convert it into a p-value with that, and you can print out the p-value and do your comparison. I've included an effect size, but let's not worry too much about that for the time being. Okay, happy with that. Goodness of fit. Brilliant. Okay, very quickly, for those who attended late, here are the codes again, if you need. Because what we can do, we can actually use the chi-square tests also to do a little bit more sort of sexy stuff. Don't get excited. We can use a different chi-square test to test whether there is a connection between two variables. And that is why this particular test is called a chi-square test for independence, because it tests whether two variables are independent of each other. Or I can turn it around and say, are two variables actually connected to each other? And here is a nice example that I have to admit I just made up. So the numbers that you see here have nothing to do with reality, but I just picked them because they are easy to handle and they illustrate the concept that we are going to use. What you see here is a table with basically, if we don't count the headers, is composed of 2 by 2 cells. So we've got 2 rows and 2 columns. This is called a 2 by 2 contingency table. Very, very frequent, this. And let's say we conduct a study and we have, say, a certain number of smokers and a certain number of non-smokers. And we test how many of these people have or present with lung cancer. As I said, these numbers are totally fictitious. I made them up just to illustrate the concept. So we have 30 smokers have developed cancer and 70 smokers don't have cancer. So we have 100 people here who were smokers. In the non-smoker group, we have 10 people who developed cancer and 90 people who have non-cancer. So that's also 100, but the numbers don't have to be the same in these categories. This is actually called the marginal totals. Marginal totals. We can also calculate the marginal totals for the rows. We can say we've got a total of 40 people who have cancer and a total of 160 people who did not have cancer. And you always want to check whether the sum here equals the sum here. And what we get is basically a total, and this is called the grand total, of 200 people. And what we want to find out now is there a link between smoking and lung cancer? From these data, can we conclude that two variables, smoking and cancer, are linked? Or we can also turn it around and say cancer is independent of smoking. Okay, So when you see these numbers, what do you think? What's your gut feeling?
My gut feeling is that that smoking is connected.
Smoking is connected. What do other people think?
30 out of 40.
Yes or yes? Or no? Is it linked? Linked? Yeah. Okay, so how can we calculate that? Again, well, we would need to formulate our null hypothesis. And I am an incredibly lazy sod, because what I'm going to do is I just simply copy the null hypothesis from above. There's no difference between the expected and the observed counts in the population. Any difference that we see can be explained by sampling error. It's exactly the same. The really nice thing about chi-square test, it's incredibly boring. You just always write the same null hypothesis and H1, alternative hypothesis. Okay, alpha. Oh, we just do 5%. And I am again. Let's just simply copy that. Copy. Just voila, job done. Right? The chi-square test statistic is exactly the same. We just have to figure it out, how to do that. Because what would we do for the expected number? That's a little bit more tricky, actually. In our example here, what we can do is actually, there's a very simple trick how you calculate the expected numbers. Let me just simply change the color. What you do for each cell that you use is you calculate the expected number by using the marginal totals, multiplying the marginal totals divided by the grand total. So you take this number here, and this number, and divide it by this number if you are looking for the cell. So we've got here 100 times 40 divided by 200. That would be your expected number. And you can think of sort of percentage in a way. Now, for this one here, you just take this one times this one. And again, you divide it by the grand total. So here you would have 100 times 40 divided by 200. For this one here, you take 100 times, now you use this one here, 160 divided by 200. And last but not least, this one here is, again, 100 times 160 divided by 200. Yeah. This helps us to calculate the expected numbers. So 100 times 40 divided by 200, that gives us a value of 20. Thank you. So this is our expected number. This is what we actually observe. This one here, 100, oh, we just calculated that, didn't we? That is 20. What have we got for these ones here? 100 times 160 divided by 200, that gives us 80. Yeah, 80. And this one gives us, same, 80. So, let me just simply copy that where we've got a little bit more space. Copy. Because now we can do our expected. So for the first cell, we get, no, we do it back in black. We get 30 minus 20 squared divided by the expected number, by 20. Yeah? So we've got observed minus expected divided by expected. The next one, it doesn't matter which order we use. We can either go down and then sideways, or sideways and down. Let's do, say, 10 minus 20 squared divided by 20. So I use this one here. Plus, let's do this one. We have 70 minus 80 squared divided by what? No? 80, exactly. Plus, and here we've got 90 minus 80 squared divided by 80. Yep, have I done it right? So here we've got 30 minus 20, that is 10, squared is 100, divided by 20, plus 10 minus 20 is the same, 100 over 20, plus that is 100 divided by 80, plus, oh, that's also 100 divided by 80. Yeah? Happy with that? Okay. What do we get for that? That would be, I've done that before, 12.5. Is that what you got? Yeah. So that is our chi-square value, is 12.5. Now we need to figure out the degrees of freedom for that. And for this 2 by 2, or generally, degrees of freedom for a table like that, again, is pretty easy to calculate. It is the number of rows minus 1 multiplied by the number of columns minus 1. So the number of rows is 2 minus 1. The number of columns is also 2 minus 1. So our degree of freedom is 1. Degree of freedom is 1. So we've got 12.5 chi-square 12.5 with 1 degree of freedom, right? Now we can put that into our Excel or spreadsheet with exactly the same equation. Chi-square dist right tail 12.5 and 1, and we get a p-value of, has anyone done that already? Oh, let's put it in.
0.001.
Aha. Let's do 12.5 and 1. And we get 0.00041, exactly as you said. So we've got the p-value 0.00041. That's our p-value. Yeah. So the p-value is certainly smaller than alpha. Therefore, what do we do with the null hypothesis? We reject the null hypothesis. So the null hypothesis said there is no difference between expected and observed. And sort of in the back of our mind, we need to say, if there was no connection between the variables. So here we reject the null hypothesis. There is a difference. Between observed and expected. This means there is a link or connection between the two variables. That means smoking and cancer are connected. We very clearly see that smokers have more cancer than non-smokers. Make sense? It's a really nice test. Mathematically, you don't really have to do a lot. It's just always the same sort of algorithm, if you like. You can easily do that on a piece of paper. Okay, finding the p-value, probably need Excel or spreadsheet or something like that for that. But, you know, that's, again, not terribly difficult. But you can do a lot with this chi-square test for independence. Make sense? Happy with that? Okay, now we can actually do even more with this table. And here is where then the really cool stuff starts. Because we can use this table to say, how much more is this link? Is it, you know, are people who smoke really in danger of developing cancer? And if so, we've just shown that, how much more? I suggest we have a 5-minute break, and then I show you how we can do that. Happy with that? So go for a wee-wee. Make sense?
I was going to ask what the, for our exam results, the average between men and women.
Sorry?
The average score grade between men and women.
I can dig that out.
Okay.
And we can test whether there's a difference between them. Good shout.
Yeah.
What's your gut feeling?
Well, I think there are more women in class, so it's more like.
Oh, we can
but
easily
right.
Adjust for that. Yeah.
I'm gonna say that women have a higher score.
Okay. Challenge accepted. Very easy to do that. What would be a statistical test? Devise a test how we could measure that.
I mean, I don't know. Maybe the default now is chi-squared because it's 10.
Okay, ask yourself the question, what is the data type?
Right, it's not the 3 because it's
Uh-huh,
up to
good.
100%.
Yes, good.
So
would be continuous. So we could use.
So is it like the well, here in week 10 I have the
it's continuous data.
It's continuous data. Do we have to know if there's normal distribution? distribution, or is it
We
more-
just simply assume it's a normal distribution.
okay?
You're on the right track.
This is what took me the longest to do the exam, is figuring out what I need
Yeah.
to do.
It's in there. It's really with me. I'm used to it with reference.
I mean, this is all still chi-square.
Don't, it's not discrete data.
Right.
I would go with that.
Ooh.
I would go with that. An independent, two-sample, two-tailed t-test, probably not the standard t-test, always go for the Welch test, but that would be exactly the test that I would apply. Well done. Statistics is fun, hey?
It can be fun and sometimes it's frustrating.
Sorry?
It can be fun and sometimes it's frustrating.
Why? Because you were wrong with the nucleotide.
Yeah.
This is, I think this is the true beauty of statistics, because you discover that sometimes you are totally out with your gut feeling, right? And I think that makes it really exciting and sort of.
Well, because if I was doing an experiment and I was seeing those values, my gut would be it's more likely that I'm going to see A's.
Yeah.
It's not statistically significantly different, but applicably when doing the project, I would still feel more inclined to.
Absolutely. But as you've seen, if you're not careful, your interpretation would not be held tight against scrutiny. So if a sort of bastard like me was to read that, I would immediately say, wait a moment, I don't believe what you are selling me.
I'm not saying that I would like falsify or say this is significant, but just in actual lab bench practice, it might.
Again,
Yeah.
this is a great thing, because you basically say, whoa, wait a moment, there is something that I didn't expect. What the hell is going on here? So you would probably be inclined to repeat the experiment. Yeah? And then you would say, the repeat experiment gave me similar numbers. It will not give me exactly the same numbers. That's sampling error.
Yeah.
Therefore, I am now more inclined to say, yes, my initial intuition. Okay, so most people are back. I don't know, missing in action, but let's crack on. Because what I want to introduce you to in the second part is, again, something that is derived from this 2x2 contingency table, and that can be incredibly useful. So we've just established that there is a link between the two variables, between smoking and cancer. And we now want to figure out how strong is this link. And there is something that people who do betting are probably quite familiar with. There's the concept of odds and odds ratios. Are people familiar with odds? You are a bookie. Okay, good. So in the bookies, you always get odds, right? What the hell is odds? Odds is just simply, and you correct me please if I get it wrong, odds is defined as the number of events that you observe divided by the number of non-events. So in a way, you are dichotomous. So for example, for a smoker, you would have the odds of developing cancer in a smoker is given by 30 cancer divided by not having cancer, 70. So the odds of developing cancer would be 30 over 70. Yeah, that's the odds. Of course, we can do that for non-smoker. For non-smoker, this would be 10 over 90 for non-smoker. Yeah, 10 develop cancer, 90 don't. And what you see here is you have to be dichotomous, event divided by non-event. Very often, we also have another term, which I want to mention here. That's the relative risk. The relative risk is defined as the number of events divided by the total number. By total. And this total number of events is basically the number of non-events plus the number of events. So in our case here, for the smoker, it would be 30 divided by 100. That would be the relative risk. Make sense? Okay. We are not now working with the relative risk. We are working with the odds. And what we can do is we can formulate an odds ratio. So in the odds ratio, we just take that is defined as the odds for, say, smoker divided by the odds for non-smoker. So in our case here, this would be 30 over 70 divided by 10 over 90. Yeah? And we can use a little bit of algebra. So that would be 30 over 70 multiplied by 90 over 10. Yeah, divide by the inverse fraction. So we would get here, that is 2,700 divided by 700, and that is equals to 3.86. Yeah? Is that right? 3.91? 2,700 divided by 700, 3.86. That's what I got.
I just did 30 divided by 70 and then 90.
But I made a mistake. No, I stick with that. Stick to my guns. So, the odds ratio, or in other words, the odds for a smoker to develop cancer compared to the odds for a non-smoker is 3.86 times higher. So if you are a smoker, your odds of developing cancer are 3.86 times higher than for a non-smoker. That is the odds ratio. Probably makes you think, should I smoke or not? But please don't forget, these numbers are fictitious, and I made them up. So if you probably look at the literature, you might even find that the numbers are, that your odds are even worse than that. Okay, so if we've got an odds ratio of 1, what would that tell us? No difference between the odds. Exactly. What can odds ratio assume? Which numbers? So we know that 1 is sort of the separating line. If we've got an odds ratio of larger than 1, it means favor of the numerator. So we favor what's up here. Odds ratio smaller than 1, we are in favor of the denominator. Yeah, happy with that? Pretty straightforward. Now, we are focused on equality. And what we see is that, in a way, if we have these categories, there is a little bit of injustice in it. Because, let's think about it. If, for example, we had a very small denominator, just say 1 in 90, and a fairly large numerator, we divide something large by something very small. If we had nobody here, we would even have 0 down here, so our odds ratio would become infinite. So here, if the odds ratio is larger than 1, it can be anything between 1 and infinity. On the other hand, if we have an odds ratio smaller than 1, let's say we have 0 here and whatever number here, here we would have between 0 and 1. Yeah? In terms of what we would get. And in a way, if you think about it, this is not fair. This guy has the possibility to go from 1 to infinity. Huge stretch. On the other hand, this guy only has the margin of between 0 and 1. That's just between 1. And that's not fair. How can we make that fair? Sorry?
I don't know. I was gonna say just flip it and then like flip the numerator and denominator.
What we can do to make it fair, that we have an even spread in both, is instead of the odds ratio, which is usually abbreviated as OR, we take the logarithm of the odds ratio. And we usually take the natural logarithm, take ln of odds ratio. So ln of the odds ratio, this is referred to as log odds ratio. Now we have between 1 and infinity, logarithm would be between 0 and infinity, if we take the log odds ratio. Log of 1 is 0, right? That's 4 larger than 1. And we would have negative infinity to 0 for log odds ratio smaller than 1. And both now have basically an entire range from negative infinity to 0 and from 0 to positive infinity for the other side. Of course, log odds ratio, ln of an odds ratio of 1, that would be 0. That's now our middle point. Yeah, makes sense? Happy with that? So what you find very often is that people who do this statistics will not report the odds ratio, they will instead report the log odds ratio. Just simply because it is much fairer. It is a sort of a better distribution. Make sense? Happy with that? So log odds ratio is incredibly useful because in our case here, we had an ln of, what was it, 3.86. That was, so our log odds ratio would be, what is ln? Let's calculate that quickly. We have ln 3.86, 1.35. Okay? So that would be 1.35. Great, we have calculated a log odds ratio. Log odds ratio of 0 would indicate there's no difference because the odds ratio is 1. In our case, we have a log odds ratio of 1.35. So that means, yes, people are at risk, at a higher, or have higher odds to get cancer when they are smoking. However, there's always a however, right? Klapper always makes things complicated. What we mustn't forget is that this is actually a sort of an estimate of the population. And if we did another sort of survey, we probably would not get exactly the same numbers. We would get another estimate for the population. And if you think back, we said we can't ever be sure about the population. For example, population mean when we measure the heights. But what we can do is we can actually calculate a confidence interval. We could calculate a confidence interval for our log odds ratio. So and we usually use a 95% confidence interval. For the log odds ratio. How can we do that? So the confidence interval would be the log odds ratio plus minus 1.96. This value is from the normal distribution because it turns out that these confidence intervals are normal distributed. 1.96 means it's 2 standard deviation away from the mean. That's the 95%. And that is basically from the normal distribution, this value, times the standard error for log odds ratio. So we've got this one here, 1.35 plus minus 1.96 times, I say, oh, bugger it, how do we find the standard error for this? And it actually turns out to be really simple. Let's go back to our table and write it generally. Let's call this cell A. Let's call this B. C, and D, just to give the cells a name. A, B, C, D. You can do it any other orientation, doesn't matter. And for the standard error, is given by this beautiful equation, 1 over A plus 1 over B plus 1 over C plus 1 over D. So that's our standard error. We can now calculate this as standard error equals square root of 1 over, what was that? That was 30. Was that 30? Yeah, this was 30. B is 10 plus 1 over 10 plus 1 over 70 plus 1 over 90. Yeah, happy with that? And if my maths wasn't totally wrong, then this gives us the square root of 0.1587. 0.1587. Did you get the same numbers?
I haven't done it yet.
You haven't done it yet. So that's our standard error. So we can now calculate. This gives actually, what is the square root of that? Roughly 0.4. So our log odds ratio, the confidence interval would be plus minus 1.96 times 0.4. Yeah. Here we had, this number was it 1.35? 1.35 plus minus 0.96 times 0.4 is roughly 0.8. Uh, 0.78. So the 95% confidence interval for LNOR, 95% confidence interval, would be 1.35 minus 0.78 and 1.35 plus 0.78. Yeah. Now, we see that this one here, does that give me, check. Zero. Is that right? 0.57 and 2.13. Yeah. If I do, yeah, that should be correct. We see that this number here is larger than 0, or the 95% confidence interval does not include the value for 0. And the value of 0 would mean there's no difference. But it doesn't include 0, so you see that there is actually a true effect. We can even go further and say why don't we calculate quickly, because with log odds, people don't really get what it means. Why don't we convert that back into odds? So all we need to do is to convert it back is convert the ln back into non-ln. We just simply take both values e to the power of. E to the power of 0.57, because e is the inverse operation of the ln. We get rid of the ln. So e to the power of 0.7. $1.78 or 7. 1.77, and the other one is 2.13. No, this one. E to the power of 2.17. $8.76. Oh, 213. Sorry, I got the wrong one. E 2.13. That's the right one. 8.41. So these are now our odds ratios for the confidence interval. And this means, in plain English, a smoker has a 1.77 to 8.41 times higher odds to develop cancer than a non-smoker. So we, in a way, we extended our chi-square test of independence, and we now can even say how much more dangerous it is with a confidence interval. And if you still smoke, bear in mind that I just made up these numbers. Does that make sense? Log odds ratios and the confidence of these log odds ratios, and then converted into odds ratios, are incredibly common in anything statistical, especially in medical statistics. You will very often find comparison of log odds ratios. You will very often find the confidence of log odds ratios. And then basically the back translation into what the hell does that mean? Happy with that? Did you learn anything today? Thank you very much. Tomorrow I will tell you all about the assessment. Go in peace, but please go. Yeah. That is just my calculator on the phone or on the tablet. It's just a normal calculator.
Does it do it?
The built-in. Yeah. You should have that as well. If you